Here we have a quartic function that we need to sketch. Now lambda is positive, so I'd call this like a positive quartic essentially. A positive quadratic will be a bit like this, sometimes referred to as like a smiley quadratic, 2 roots. A positive cubic with 3 roots would look like this, which means if we get a quartic, it goes back to going to infinity as x goes to minus infinity. It'll come down and it will look like that. 1, 2, 3, 4 roots. So we need to find these roots, and we can do that because we can factorize this function fully. It's going to be 1 over lambda, and then we've got 2 lots of a difference of 2 squares. X minus 2, x plus 2, x minus 5, x plus 5. So we're going to have just roughly like minus 5 and 2, and then 2 and 5. So it's going to look a little bit like that. 5, 2, minus 2, minus 5. We get these roots by essentially setting it equal to 0, this thing equal to 0, and then you just take the negatives. And finally, we asked where it crosses the coordinate axis. I've not added this one on. So that would be, if I was to multiply the minus 4 and the minus 25 by 1 over lambda, we're going to get 100 over lambda. Okay, good start. Next up, we're asked to find in terms of lambda the range of f. Well, we can see that there is no maximum value. It's just going to go off to positive infinity. So we need to work out the minimum. Now, it's not a quadratic, so we can't use a difference of 2 squares or anything like that. What we can do is we can use that other method for calculating stationary points, and that is to differentiate it and then find the minimum. So we've got df. Well, actually, I need to first of all expand it, don't I? So I'm going to get x to the 4 minus 29 x squared plus 100, and I'm multiplying that by 1 over lambda. So I can just carry that through. Like I could multiply by it, or I could just sort of have it here. And that is going to equal 0 for stationary points. So this is just a constant, so it must be that 4x cubed minus 58x equals 0. And I can factorize as much as possible out. So 2x, because 4 doesn't go into this. Technically, this is sort of like a difference of 2 squares. So I'm going to get rid of that 2. Okay, so this will be root 2x minus root 29 and root 2x plus root 29. basically, I'm using the fact that a squared minus b squared is a plus b, a minus b. So this technically is root 2x all squared, which is why I've replaced it by root 2x here. That my a is root 2x, because then a squared is 2x squared. In any case, we're going to get that x is 0, root 29 over root 2, or minus root 29 over root 2. And we can see from the graph that x equals 0 would give us the maximum, and the other two will give us minimums. So min when x is root 29 over 2. And here, f of x, now we need to decide what bit we substitute it into. Do we substitute it into here, or maybe this this original factorized form, because we're squaring the third, and so it will be a bit, I think this will be a bit nicer to deal with. So it's going to be 29 over 2 minus 4 times 29 over 2 minus 25. Okay, let's get it over common denominator. Now 21 times 21, you might know off the top of your head it's 441, otherwise you're going to have to figure that one out. So we're going to get 441 over 4 lambda with a minus, and therefore range, we're there basically, range of f of x is that f of x is greater or equal, we've just found the minimum, so it's always this or more than that. Okay, that is our answer. Good work so far. Finally, on to part C. It says find the sets of positive integers k and lambda such that the equation k equals the modulus of f of x has exactly k distinct roots. I'm going to bring this down. This looks like it's going to be the trickiest bit. It is worth more marks than the other two bits combined. Okay, first things first, let's get a sketch down again. So first of all, we had that it was minus 441 over 4 lambda. And that is going to, well, the key thing is that is going to be greater than 100 over lambda. So when we take the modulus, this negative bit will flip and be larger. Okay, this is going to be quite important, I think, because it definitely impacts on the number of roots that we're going to be able to have. So first of all, let's look at k equals 0. And then if we've got that, the modulus is equal to this, then actually it would be here. And we don't get 0 roots, like there's no distinct roots, so no solutions here. There's not going to be any solutions for k equals 1 either, because this is symmetric. So the next thing to look at is when k is equal to 2. And that is going to be if we manage to get above here. So say over here. And to get 2 solutions then, we need that 2 has to be greater than this maximum, this local maximum, greater than 4, 1 over 4 lambda. And that's going to mean that 8 lambda is going to be greater than 441. So if we do a short division, eights into 40 go 5, remainder 4. 8 into 40 again, remainder 1. So lambda has to be greater than 55 and 1/8. Now, don't forget that lambda actually has to be a positive integer. So for k equals 2, we need that lambda has to be greater or equal to 56. That's our first one done. Let's take a look at k equals 4 now. So we need 4 roots. Well, we have 2 here. If you go below, then we're going to get 6. The only way we can get 4 is if it just touches here. Arguably, this would still be 6. I don't know if you count that, because this is technically a double root. But let's go with it. So k equals 4. We'd have to get that 4 is equal to 441 over 4 lambda. So lambda would equal 441 over 16. And this is not, like 4 doesn't go into this, so 16 isn't. So not an integer. No solutions. I suppose we don't need to put a box around it. We're only interested in where we do get solutions. Moving on then. Okay, if we keep going down, that's when we can get 6. So we'll get 6 here, all the way up to here. So it's going to be between these two values. So it's got to be greater than 100 over lambda. But less than 441 over 4 lambda. We can multiply through by lambda and divide through by 6. So lambda, remember, lambda's constant. So 100 over 6 will be less than lambda, which will be less than 441 over 24. Nine over 24, 3/8. So that gives us solutions from this. Lambda is going to equal 17 or 18. We could write that as an inequality, but it makes sense to just write the two possible values. Remember, that is when k is equal to 6. If we keep looking, then as we get to here, there would be a root here, so you'd get k equals 7. So then 7 would equal 100 over lambda. And this has no solutions as well, because you can't find a number that does that, where lambda is an integer. So finally, that just takes us to, where's it gone? Here we go. If we go below, then we can get 1, 2, 3, 4, 5, 6, 7, 8 solutions. So k equals 8, and that would be when 8 is less than 100 over lambda. So lambda is less than 100 over 8, which if I divide top and bottom by 4 will be 25 over 2, 12.5. So remember, lambda has to be a positive constant, so that's going to leave us with 0, less than or equal to lambda, less than or equal to 12. Okay, those are all our solutions. K equals 2, K equals 6, and K equals 8. Well done if you managed to get that.